All right, let's get started. I hope you guys are doing well. All right. This today's lecture, I just want to introduce some basic concepts of modeling, because that's what a lot of our course will be focused on different algorithms and statistical models that we use to, try to um, figure out problems and, solve data related issues. So, let's just talk about models and machine learning. So, what is machine learning? This is just copied from Wikipedia, and Wikipedia updates its entries, but it defines machine learning as the scientific study of algorithms and statistical models that computer systems use to effectively perform a specific task without explicit instructions, relying on patterns and inference instead. And the way I interpret this is that we try to fit models to the data. Okay. Even though it says it performs things without using explicit instructions, people still have to make a lot of decisions regarding the specifications of the model. But a lot of other decisions are going to be guided by the data and the algorithms that are used. Okay. And so the decisions that are made by those algorithms, that is the part where the quote machine is learning. And so, with the advance of AI and all kinds of different tools and things out there, I'm not so worried that all of our jobs are going to disappear and be taken by AI. Certainly, I think um, a lot of our decisions and a lot of our the things we do will be augmented by AI, and we will kind of adapt and change things around. But I think humans will still play a role as far as making certain decisions in terms of how to specify the model and things of that nature. Um, we keep throwing this term model around. And so, I think it's helpful for us to just talk about what is a model in the first place. Okay. So here is a picture of a model airplane. And, whether we're talking about a model airplane or a statistical model, we can think of a model as a simplified representation of something complicated. Okay. So the toy airplane, the model airplane is a simplified representation of, a very complicated real life airplane or aircraft. Okay. And when we talk about statistical models, it's going to be a simplified representation of a real life, real world process, oftentimes quite a bit complex that generates data. So in real life, there are systems and processes that generate data, and we are trying to figure out a simplified model that what do you call it? That explains where these values are coming from. Sorry, give me a second here. Um, okay. And so, when we talk about a statistical model, we imagine there's some kind of process that generates data in the real world. And that's going to be, a complicated thing with, a whole bunch of different variables and things going into, determining and establishing the different values that we end up seeing. And a statistical model is going to be, a simplified version of the relationships between those variables. Okay. And so it's only going to include, maybe a subset of the variables related to the outcomes. And there's always going to be an error term to account for everything else. Okay. Um, Now, whenever we are dealing with a model, there's a kind of a quote that says, all models are wrong, but some are useful. Okay. And basically what that means is that all of the models we use don't tell the whole story. Okay. They only give us, some aspect, okay, that perhaps explains some of the things, but it's not going to tell us the whole story, okay? But they can still be useful, all right? And as far as our statistical models go, we have, I would say there's two kind of primary uses. And one is we can use models to try to make predictions. And then we can also use models to try to gain understanding of some of the relationships that exist between the variables. And a lot of times we have to make a choice regarding which of these kind of goals are going to be more important, which one we want to prioritize. Right. Um, I'm going to use an example from our textbook. So again, our textbook is a first course in machine learning. It's linked in the syllabus. Oh, by the way, I have finally posted the syllabus, and I apologize for the delay, but it's available here now in the modules. And your first homework assignment is kind of due, I think by Friday, where you will just agree to the kind of collaboration policy and academic integrity agreement here. But the syllabus keeps getting longer each quarter. But anyway, there is. Here's our textbook here, okay? And I try to use textbooks that are freely available, and unfortunately, I couldn't find one that I really liked. So, unfortunately, this is one that you do have to purchase or find somewhere. But this is the textbook. Okay, but anyway, we are going to and we're going to take a look at an example from the textbook, and here we are looking at data points from the Olympics, where one of the exciting events is the 100 meter dash, and this is usually the winner is declared the fastest fastest person on Earth. And we look at the gold medal time at the Olympics for the men's 100 meter track and field event. And in the real world, there are a whole bunch of different things that ultimately factor into the winning time. Certainly who is the person running, and what were the track conditions, and all kinds of different things. But we're going to just make a very simple model, and we're going to just kind of plot um, the year in which the event took place and the gold medal time. And what we see is just that it seems like the the winning race times seem to be getting faster over time. Okay, and I think we have data dating all the way back to 1896 up to I think 2012. So it's a few years old now. But these are kind of the winning race times. And and so a simplified model could just say, as time has gone on, right? As the years have gone by, the winning race time goes down. Okay. And so our model, our very kind of simple model is going to be something like this. Race times have gotten faster, over the years. And we're going to just fit a linear model. And I know you are all kind of very familiar with linear regression, but we're going to start here with a place that you are familiar with, so that we can kind of introduce a lot of these machine learning concepts to in a context that you are familiar with. Okay, so the idea here is that if we know the year of the Olympic Games, we might be able to make a prediction for what the winning race time was. Okay, and a linear model implies that the amount by which we're going to adjust our prediction is going to remain a constant through time. So that means if I predict the time improves by, say, 0.05 seconds, if we go from 1920 to 1924, then it also means that, 80 years later, if I go from the year 2000 to 2004, I'm going to improve my prediction or reduce my prediction by that same amount of 0.05 seconds. Okay, and that's the linear model, is that this kind of rate of adjustment remains constant throughout the entire data set. Okay, now this obviously cannot work for predicting values in the distant future, because in the distant future, then that means we could end up with a negative time. So obviously, there is going to be a limit to this. But the as far as perhaps within the range of data where the range where we've collected data, this model could be useful, as far as trying to, if we had to guess what the winning race time would have been in, say, 1940 or something like that. Okay. It could still be useful. And so what we're going to do is we're going to try to fit a straight line to the data. And when we do that, there are two parameters that we have to estimate. We have to estimate a slope and we have to estimate an intercept. And when we talk about fitting a model is the process of estimating these model parameters. In our case, it's a slope and intercept. In other more kind of complicated models, you might have hundreds of parameters, maybe thousands of parameters. In a big neural network, you might have millions, possibly even billions of parameters and weights to estimate. And so when we talk about fitting the model or training the model, it really just comes down to estimating what those model parameters are, whether it's two of them, slope and intercept, or whether it's a billion of them with, all of the different weights in a, deep neural network. Okay. And so when we try to estimate the values of our parameters, we want to do it in such a way that the resulting model does the best job of fitting the data. Okay. We want it to do the best job of fitting the data. And so we have to define, what does it mean to do the best job of fitting the data? And um, so this is where we have something called the objective function, okay, or the cost function, or the loss function, or something. It's basically the thing that defines our goal, and this is the concept. An important concept in machine learning is that you have to kind of tell your computer, or tell the machine, or tell the algorithm, this is the goal. This is the thing that I want you to strive for. Okay. And it's oftentimes it's a simple rule, but certainly we're going to start off with a simple objective function, and they can certainly become, more complicated. But yes, we say this is the thing. This is how we define success. This is the thing that we want, um, to strive for. Okay. And so when we say we want the best parameter estimates, how we define that word best is going to be very important. And that's carried out through our choice of an objective function. And so for linear regression, okay, we often also call it ordinary least squares regression. And that means we've defined the best model as the model that minimizes the total squares of the residuals. Okay, so residual is the difference between the actual value in our data and what our model predicts. And so we're going to say the residuals, basically how different our prediction is from the actual value. And we want to minimize the total squares of the residuals. And so this is our objective function. We say, here's the actual value, the y. Here's our prediction, y hat, okay? And we have them for each of our n observations. So each residual is going to be y sub n minus y hat sub n. We take that difference, that's the residual. We're going to square it, and then we add it up for all of our n observations, all right? And so that's going to be our residuals sum of squares, and we want to minimize the total residual sum of squares. So we call this the objective function, okay? And in this case, because we try to minimize it, sometimes this is also known as a loss function or a cost function, because we want to minimize our losses or minimize our costs. Okay, so these are things that we want to kind of minimize or shrink. And this is how we define what is the best. And and in general, a lot of our machine learning methods, okay, so linear regression will kind of fit under that. Um, a lot of these models try to fit parameters by trying to minimize an objective function. Sometimes we try to maximize an objective function. So there are other methods where we want to maximize like the likelihood or something, okay? So we have different kinds of objective functions and we say this is how we define success. Either we minimize this thing or we maximize that thing or something like that. And so a lot of our machine learning problems can be framed as optimization problems. Okay. And even though linear regression is review for you, we're going to start here just to kind of get us familiar with a lot of these concepts in machine learning. All right, let me go ahead and give you your first view quiz answer for today, which is the letter B. B as in bear. B is our first view quiz answer. Okay, so when you read that textbook, A First Course in Machine Learning, it uses, in my opinion, a kind of a uh, unique notation for some of the letters. It's not that unusual, okay? It tries to take kind of a universal approach. So when we're talking about slope and intercept, a lot of times in linear regression textbooks, the slope and the intercept are, slope is beta 1 and intercept is beta 0. In our textbook, the machine learning textbook, it says it uses the parameters W0 and W1, W for weights, because that's just kind of a generic term, not just for linear regression, but for any kind of model. You can just have different weights and different parameters, and so they just use the terms W0 and W1. Okay. The actual values are denoted with a T rather than a Y. So Y sub n is not, we don't use that. We use T, T for target, like our target value. That's the thing that we're trying to hit. Um, and, um, and then so we say the predicted values are determined by a function, and it's a function where the input value is going to be x sub n, our input value, along with the given parameters or the figured out parameters W0 and W1. Okay. And then our textbook also uses the mean squared error rather than the total squared error. Okay. And the only difference between the mean squared error and the total squared error is you take your total squared error, you divide by how many observations you have. So it's just total squared error divided by n. Okay. And, whatever solution minimizes the mean squared error is going to be the same thing that minimizes the total squared error, your residual sum of squares. So this loss function, we're going to write as fancy L, okay, for our loss function is going to be, 1 over n times basically our sum of squared residuals, which following the textbook notation is going to be found by doing T sub n, or target value, minus F, basically the model that we're fitting, the function F x of n given our parameters W0 and W1. Okay, we take that difference, we square it, we sum it up, divide by n. So that's our textbook's notation. Okay, uh, another kind of loss function that we see is the root mean squared error, or the RMSE. And all it is the exact same thing as the mean squared error, but you just take the square root of the whole thing. Okay, you just take the square root of basically your mean squared error. And, because the square root function is monotonic, right? Everywhere where a is greater than b, then the square root of a is also greater than the square root of b. Then that means whatever value that minimizes the mean squared errors will be the same values that minimize your root mean squared error, your RMSE. So this is often a thing that we see, and the reason why is because the units of root mean squared error is going to be the same as the original units versus when you're dealing with squared errors, your units are squares. So for example, if you're dealing with dollars, your total squared error, the units there are square dollars, which is kind of a weird concept, whereas root mean squared error, your your errors will just be will have the unit dollars, which makes more sense, right? But I don't know what a square dollar is, but that's what happens when you square. If you square $7, you get 49 square dollars. And that feels funny, but it's a thing. Okay, so anyway, our linear model, we've got the slope, we've got the intercept, W0 and W1, W0 for the intercept. And the value we're going to predict is going to be our intercept plus our slope, W1, times our input value, x of n. And so plugging that into our loss function is going to be our target value minus the quantity W0 plus W1 x of n. We're going to take that difference and we're going to square it, add them all up. Okay. And this is what we have. And we can try to figure out what values of W0 and W1 we should do. Now we could do this with calculus, right? And so when we do that, we would take our observed data, the x values and our target values t, and we treat those as fixed values. And the value of our loss function depends only on the two model parameters, W0 and W1. We want to find the values of these arguments, W0 and W1, which will minimize the loss function for our observed data. And so the values that minimize the loss function for our particular data set, we're going to call W0 hat and W1 hat. Okay, these are the ones that will happen to minimize this total squared error or the mean squared error for our particular data. And so we're looking for the W0 and the W1 that's going to minimize it. So that's argmin over W0 and W1. And in order to solve this, we would expand this out. So if you do, basically, if you expand all of this out, you're gonna get this thing, right? So first, outer, inner, last, and you have to do the whole kind of thing. And then the way we would solve this using calculus is you would take the partial derivative of this loss function with respect to W0 and W1. You set those partial derivatives equal to 0. You have basically two equations and two unknowns, and you solve for W0 and W1, okay? And I'm going to kind of skip a bunch of the work, but basically here it is in calculus. If you take the partial derivative with respect to the slope, you get this. If you take the partial derivative with respect to the intercept, you get this. The full work of this thing can be found in the textbook. And basically we set these things equal to 0 and we solve and we will get our estimates for what W0 hat and W1 hat are. Okay. And that's that. And I think if you've taken Stats 100C, you work through this. And if you haven't taken that yet, and you will, and then you'll work through all of this, and you'll see basically this is how we solve our linear models. Okay. Now, one thing is that it is useful to kind of, instead of having to deal with the summations and all kinds of stuff like that, it's a lot of times useful to work with kind of a linear algebra notation. Okay. So, we've got a bunch of observations. We have a summation term in the loss function because we have to kind of sum, the values for all of the different n observations that we have. And that could end up becoming a little bit annoying to deal with. So what we're going to do is we're going to switch over to linear algebra. And when we use linear algebra and have matrices, then when you multiply matrices together, a summation is kind of part of that matrix multiplication, right? If you take a vector and you take another vector and you multiply them together, you are multiplying each element and then you're adding them all together. If it's been a little while since you've taken linear algebra, whether it was, I think 33A or, later on you might take Math 115A where you have to prove some of these things. I highly recommend this playlist from Three Blue, One Brown, which is it's an excellent channel, and this playlist covers, reviews some of the things in linear algebra, provides visual explanations for a lot of these things, which I think is really great. Okay, but anyway, so what we're going to do is we're going to approach the same problem of ordinary least squares regression, but we'll do it in matrix notation here. Okay. And so here, actually, let me go ahead and give you your second view quiz answer. Our second view quiz answer today is the letter A. A as an apple. A as an apple. Okay. Um, so we have our parameters, our slope and our intercept, and we're going to gather them together into this vector W. Okay. And then each observation that we have is basically just our input value is x sub n. But in order to kind of get it to multiply with my vector w, I'm going to tack on a 1, okay? And then that's going to be for the intercept. And thus, when we talk about the intercept plus the slope times x, I can say that's going to be the result of doing w times x sub n, right? W transpose xn. I've got the w0 and w1 multiplied by 1 and xn, so we would get w0 times 1 plus w1 times xn, and the value predicted in my model would be this, W transpose X of n. This is just one observation, the nth observation in X, and the entire matrix for all n observations that I have, okay, will be big X, and that will be this thing. I will have n rows, okay, and so I will have a column of ones and a column of X values, X1, X2, all the way down to Xn, and thus I can take all of my predicted values will be X times W, right? And so the entire loss function, which is this thing over here, can be expressed in matrix form as doing T minus XW transpose times T minus XW, T being our target values in a column matrix. And so kind of the expansion of this, or the explanation of this, can be found by doing this, right? So here I can say, what is X times W? X times W. So if I have my matrix of X, which is n rows by 2 columns, and I multiply it by my vector W, okay, which is 2 rows in 1 column. When I multiply X times W, I'm going to just get n rows in 1 column, and this will just be, each predicted value, W0 plus W1 times X1, W0 plus W1 times X2, so on and so forth, up through that, okay? Now, sometimes when you're dealing with matrices, the order in which you do multiplication matters, right? And when you're dealing with just kind of real numbers, scalar values, whether you do A times B or B times A, that's exactly the same. It doesn't matter. But with matrices, you can multiply X times W, but you cannot write multiply W times X, okay? And so in order to kind of help you keep track of this, I strongly, strongly, strongly recommend that you always write the dimensions underneath each matrix. And this will kind of help you make sure that your dimensions align. So X is n rows by 2 columns, and W is 2 by 1. And so when you see it like this, you can say, okay, I can do X times W, because basically the inner dimensions, the number of columns in this matrix matches the number of rows in this matrix. And so when you do an n by 2 matrix by a 2 by 1, you're going to get an n by 1, and that works, right? If you had them swapped around and you have a 2 by 1 times an n by 2, you're going to get dimension mismatch. So anyway, I strongly recommend this. This is what we have. This is our predicted values. Our n predicted values are going to be xw. So to do this in, say, R, I would take, I can just C bind column bind a column of ones with my X values. Okay, so my X values are just, I've got 28 observations, and so now X is going to be a column of ones along with a column of my X values, and then W I'm going to just have being kind of like my my two parameters here, two rows, one column there. And you can see when I try to do something like this in R, I can do X times W. This is our matrix multiplier operator. So X matrix multiply W, the result is going to be N by 1, 28 by 1. However, if I try to do W times X, I get this error, non-conformable arguments. And this is going to be a common error. And what this means is that your matrices, the dimensions don't align. If you try to do W times X, you're doing a 2 by 1 times an N by 2, and R says you can't do that, okay? And that's what non-conformable arguments mean, okay? All right, so anyway, XW is my column of predictions, and therefore my column of residuals is just going to be my vector T minus XW. So my vector T is going to be all of the N target values. I've got T1, T2 up through Tn, and then my predicted values are X times W. And so this worked out. T minus XW is a column, N rows, one column here, and that's what we have. And then thus my sum of squares, okay, the sum of squared errors can just be expressed as T minus XW transpose times T minus XW. Because if I take this column and I transpose it, then I get T1 minus my predicted value, and then T2 minus my predicted value for X2, and then all the way up to this. And then I have my column of values here. And then thus when you multiply this, we take the first element and you multiply them together. Then you take the second element and you multiply them together. That's basically you're squaring each element. And then with the matrix multiplication, you multiply these things and then you add them all together. So this is effectively just squaring and summing all of my elements. So if I do T minus XW transpose times T minus XW. And then if I multiply this entire thing by 1 over n, then I get my mean squared error. Okay, so T minus XW transpose times T minus XW, that's going to result in a 1 by 1 scalar value. I multiply that by 1 over n, another scalar value, and so my loss function is just a single scalar value, a 1 by 1 scalar value, which is exactly what we want. Okay, so this is what I have. I've got T minus XW transpose times T minus XW, and I can expand this out. And so with the transpose, you distribute the transpose and you get T transpose minus XW transpose. The transpose of a product is basically the product of the transposes. So this becomes T transpose minus W transpose X transpose. We're still multiplying this by T minus XW. And then we multiply this out. And so kind of following our multiplication rules, I do first outer, inner, last. So I get T transpose T. And then I get T transpose XW minus W transpose X transpose times T, and then W transpose X transpose XW. Okay. T transpose T, this is a 1 by n by an n by 1. That's going to be a 1 by 1. This whole thing, T transpose is 1 by n, X is n by 2, W is 2 by 1. This whole thing also multiplies down to a 1 by 1. Same thing over here, I have a 1 by 2, W transpose is 1 by 2, X transpose is 2 by n, and T is n by 1, so this all lines up, and that becomes a 1 by 1. And then over here, W transpose X transpose XW is a 1 by 2 by a 2 by n times an n by 2 times a 2 by 1. And so that whole thing also becomes a 1 by 1. So everything aligns. These are all 1 by 1s. And then I can combine these two things, okay, into 2W transpose X transpose T. And the reason for this is that this and this are just transposes of each other, right? T transpose XW is the transpose of W transpose X transpose T. And because it's a scalar, a 1 by 1, a scalar, a transpose of a scalar is still a scalar. that means these two things are identical, and I can just combine them. Okay, I can just combine them. So our loss function can be expressed as this, with everything expanded out, and I multiply it by 1 over n to get my mean squared error, and so this is my loss function. Okay, um, and so now that we have this, the reason why we want to do it this way is because now we can do some vector-based calculus, and we can take the derivative with respect to the vector w, okay, and we can set that equal to 0 and solve for w, okay? So we've defined our loss function in matrix notation. We still want to find the value of w that's going to minimize the loss. So we're going to take the derivative with respect to the vector w. We'll set that derivative equal to 0, or I guess in this case, the gradient. We'll set that gradient equal to 0 and solve for w. And so we'll do a little bit in kind of vector-based calculus. Um, and so if we're dealing with just real numbers, derivatives can be found as kind of like the slope of your tangent line. And the way we figure out a derivative is we say, okay, well, if I imagine adding a tiny little h value to x, I ask how much does the function f of x change from f of x to f of x plus h? And then we say, okay, well, how much does that function change? And we divide by h, and we take the limit as h goes down to 0, and that's going to be the value of our derivative. Basically, we do something very similar, but now we're dealing with um, multiple values, not just a single value. We're not going, our function doesn't go from one real number to one real number, but we're taking in an input of a vector of real numbers. So in our case, we have a vector of length 2. We have a slope and an intercept. But the resulting function is still a single scalar output. It's our loss, right? So our loss function is this quantity here is just a single scalar value. It's just a 1 by 1. So we're going from two input values, the slope and the intercept, and we want to find and we get a single loss value. And so we want to say, okay, well, what if I add a tiny little h? Okay. Um, and in our case, our h exists in 2 dimensions. And we want to kind of shrink that down as that thing goes down to 0. What is how much does it change? That's going to be our gradient. Okay. It's kind of like our multi-dimensional derivative. And you can think of the gradient. The gradient is really kind of the vector of partial derivatives. Okay, what is the derivative with respect to your first weight? What's the partial derivative with respect to the second weight and things like that? But you can kind of treat it, and so you'll get a vector of partial derivatives, and that's our gradient. Okay, so the gradient represents the kind of the slope of the tangent of the graph to the function. I guess more precisely, the gradient points in the direction of the greatest rate of increase of the function. The magnitude of the gradient is the slope of the graph in that direction. And here are a few kind of useful gradient relationships that if you have a function that takes into say some kind of vector, a function of a vector, and this is what we have. We have a loss function. You input different values of your slope and intercept, or some kind of vector, and you get a scalar value. And you say, okay, well, what is the gradient, okay, or the derivative of f with respect to w? What is the gradient there? So if your function is, say, w transpose x, okay, where w is a 1 by 2, x is a 2 by 1, the gradient with respect to w is going to be just x. If you have x transpose w, the gradient with respect to w is also x. If you have w transpose w, you get 2w. If you have w transpose times some matrix C times w, the gradient with respect to that is going to be this, 2 times CW. Here is just kind of a small proof of this. So if you have W is, this vector W1 and W2, and X is X1 and X2. W transpose X is going to be W1 X1 plus W2 X2. And then if we say, okay, well, what is the gradient of this? We'll take the partial derivative with respect to W1, and then the partial derivative with respect to W2. The partial derivative of this thing with respect to W1 is just going to be X1, right? Because this thing zeroes out. There's no there's no W1 term over here. So this thing just becomes X1. What's the partial derivative of this with respect to W2? That's just going to become X2. So the gradient with respect to W of this thing just becomes X1 and X2, and that's just going to be X. So therefore, the gradient of W transpose X the gradient with respect to W is just going to be X. Okay, same kind of deal here. If I have W and I do W transpose W, I get W1 squared and W2 plus W2 squared. And if I take the partial with respect to W1, I'm going to get 2W1. If I take the partial with respect to W2, I'm going to get 2W2. And so 2W1 and 2W2 is equal to 2 times W, right? And you can kind of derive it for any of these other ones. You're going to find all of these relationships also hold. Okay, so going back to ordinary least squares regression, this is what we have, our loss function. If I distribute the 1 over n term, our loss function is 1 over n, t transpose t, W transpose X transpose t, and then W transpose X transpose X. We're going to take the gradient of this with respect to W. Okay, this thing has no W, so that becomes a 0. This whole thing, W transpose X transpose t with respect to W just becomes X transpose t times 2 over n. And then this whole thing, W transpose X XW, this becomes X transpose XW times 2. Okay, and these are all reduced down to 2 by 1 because if W itself is a 2 by 1 vector, then the gradient must also be a 2 by 1. Oh, by the way, this upside down triangle, this is read as nabla F. Okay, so the gradient with respect to W is also going to be a 2 by 1 matrix, and that's exactly what we have here. Okay, X transpose T is 2 by 1. X transpose XW is also 2 by 1. And so this is what we have. Okay, so that is my gradient. I'm going to set my gradient equal to 0, and then I'm going to solve for W. So if I set this equal to 0, and I solve for W, I can add X transpose T, and then multiply both sides by n over 2. And then so I get X transpose T is equal to X transpose XW. And I need to isolate W by itself. Now, and there's no such thing as matrix division, but you can multiply by matrix inverses. So I can't divide by a matrix, but I can multiply by a matrix inverse. So I'm going to multiply the left and right hand side by X transpose X inverse. Okay, so if I do X transpose X inverse times X transpose X, this becomes the identity, and I just get W over here. And on the left-hand side, I get X transpose X inverse times X transpose T. And that's what we have. Okay, so X transpose X inverse is going to be a 2 by 2 matrix. X transpose T is going to be 2 by 1. And so the result is this. And therefore, the value of W that I can use so that the gradient is equal to 0 is X transpose X inverse times X transpose T. And that is going to be my solution. This is the estimated value of W that's going to minimize the loss function of ordinary least squares regression. Our W hat is going to be this quantity, X transpose X inverse times X transpose T. Okay, so that was kind of a lot. This is I guess our introduction to approaching, a problem like linear regression that we're familiar with And we're going to frame it as an optimization problem. We say this is our goal. We want to minimize our sum of squared residuals. And we can do that using calculus. We can do it with partial derivatives, set our partial derivatives equal to zero and solve. But we can also use linear algebra. And again, when you're doing, vector-based calculus in the beginning, it can feel like there's a steep learning curve. But again, as you just like anything else in life, the more you use it, the more familiar you become with it. And so that's what we have. So we will pause here and we'll wrap up our lecture here today. Let me give you your last view quiz answer, which is the letter B. B as in bear is our last view quiz answer. And so we'll go ahead and end here, and we'll continue on Friday, with more concepts here regarding machine learning and objective functions and things of that nature. Okay, have a great rest of your day, and we'll see you Friday.